Picture a single cell in a database table. It holds one value, the name of a chemical element, and right now, that value is gold. A moment ago it was californium, and before that silver, then titanium, and at the very beginning, iron. The obvious assumption is that the database only remembers the current value, gold, and that the older names are simply gone, overwritten, and lost. That assumption is wrong. Underneath, the database has quietly kept a trail leading back through every version this cell has ever held. If a transaction asks for the old value, the database can reconstruct it, rewinding the cell to the way it looked minutes or even hours ago. This is the strange power at the heart of MySQL's storage engine, InnoDB. It behaves less like a filing cabinet that overwrites old papers and more like a time machine, one that lets different users read the same row and each see a different moment in its history. The mechanism behind this is called multi-version concurrency control, and once it is understood, a great deal of mysterious database behavior suddenly makes sense. To see why a database would bother keeping the past, consider what happens when many people use it at once. One transaction begins reading a long report, while, at the same moment, another transaction is busy changing rows. If the reader simply saw whatever value happened to be current at each instant, its report would be incoherent, stitched together from different points in time. What the reader wants is a single frozen view of the whole database as it existed the moment the reading began. InnoDB provides exactly that, and it calls the frozen view a consistent snapshot. In the default isolation level, known as repeatable read, the first read inside a transaction establishes this snapshot. From then on, the transaction sees the database as it was at that instant, no matter how many other transactions commit changes in the meantime. The element cell might advance from silver to gold for everyone else, yet a transaction whose snapshot was taken at silver will continue to see silver until it finishes. The tool that makes this possible is the undo log. Whenever a row changes, InnoDB writes a small record describing how to reverse that change. An undo log is best thought of not as a stored copy of the old row, but as a precise instruction. To go back one step, take the current value and apply this reversal. These instructions are what let InnoDB satisfy 3 of the 4 ACID guarantees. Atomicity comes from being able to undo a half-finished transaction, while consistency and isolation come from the ability to show each transaction its own private, stable version of reality. Here's where the mechanism becomes surprising. InnoDB does not keep a complete copy of every past version of a row sitting in the table. The table itself holds only the current value. What it keeps instead is the chain of undo logs, each one linked to the one before it, forming a path that runs backward through the row's history. Suppose the element cell has moved through 5 versions. From version 1 up to version 5, the value the table shows today. A transaction holding an older snapshot does not find its version waiting in storage. Instead, InnoDB takes the current row and walks the chain, applying one undo instruction after another. It reverses version 5 back to version 4, then version 4 to version 3, and continues stepping backward until it reaches the exact version the snapshot is entitled to see. The old row is never retrieved from a shelf. It is reconstructed, rebuilt on demand from the present value, and a sequence of reversals. This is the time machine made concrete. The current row is the present, and the undo chain is a strip of film running backward, each frame an instruction for how the previous frame differed from the next. To show a transaction in the past, InnoDB plays the film in reverse for as many frames as the snapshot requires. These undo logs are not written straight to disk and forgotten. They live first in memory, inside the area InnoDB uses for caching, called the buffer pool, and are flushed out to disk periodically. That keeps reconstruction fast when the relevant history is recent and still resident in memory. There's also a cleanup side to the story. Old versions cannot be kept forever, or storage would grow without bound. Once a transaction commits and no remaining active snapshot could possibly need a given old version, InnoDB is free to discard the undo logs that describe it. This housekeeping step is called purge, and in a healthy database it runs continuously in the background, quietly sweeping away history that no one can see anymore. Now, the consequence that catches engineers off guard. If reconstruction means walking a chain of undo logs, then the longer that chain becomes, the more work every read has to do. And the length of the chain is governed by something most people never watch, a metric called the history list length. The history list length counts how many old row versions are still being kept because some snapshot might need them. In a busy, healthy database, this number stays small because purge keeps clearing away versions the moment they become invisible to everyone. But purge can only remove a version once no active snapshot depends on it. A single open transaction holding a snapshot from an hour ago forces InnoDB to preserve every version created since that snapshot was taken across the entire database, not merely the rows that transaction touched. This is the genuinely counterintuitive part. One innocent statement, a simple select left sitting inside an uncommitted transaction, can prevent the cleanup of millions of row versions that have nothing to do with it. The transaction acts as an anchor dropped into the past, and the whole river of history piles up behind it. The cost lands on every reader that holds an old snapshot. When the history list length is large, reconstructing a single row can force InnoDB to slog through hundreds or even thousands of undo log pages, chasing the chain backward one link at a time. A read that ought to touch one page of memory ends up touching hundreds. A query that normally returns instantly begins to crawl. Reading the element cell as it stood at iron, long after the table has moved on to gold, can mean replaying the entire chain of reversals just to recover that one ancient value. This behavior is specific to repeatable read. A different isolation level, read committed, takes a fresh snapshot on every individual read rather than holding one for the whole transaction. Because each read sees the latest committed data, old versions stop being needed almost immediately, and the long chains never have the chance to accumulate. The same database run under a different rule about what a transaction is allowed to see sidesteps the entire problem. The danger stops being abstract when the chain grows long enough to topple a real system. Consider a production MySQL instance running in the cloud that appeared, by every ordinary measure, to be perfectly healthy. Underneath, a single transaction had been left open for 4 hours. For all 4 of those hours, InnoDB faithfully preserved every version of every row changed anywhere in the database, because that one ancient snapshot might still ask for them. The history list length climbed and kept climbing. As a rough guide, a value above 100,000 is treated as a serious warning that performance is about to fall apart. This instance sailed past that mark and reached 200,000. By then, the overhead of maintaining and walking those enormous chains had grown so heavy that the database could no longer keep up, and it crashed. Recovery took 2 hours, during which the system was effectively offline. A single forgotten transaction, costing nothing in itself, had quietly mortgaged the stability of the entire instance. What makes the story instructive is that nothing exotic caused it. The culprit was an ordinary pattern that appears in production again and again. The first form is the abandoned transaction, a connection left open without a commit or a rollback, anchoring history in place. The second is transaction bloat, packing far too many changes into one transaction so that an enormous load of undo logs builds up before anything is finalized. The third is simply not watching the history list length at all, so the warning signs pass unnoticed until the moment the database falls over. In each case, the underlying error is the same. The time machine is being asked to hold the past open far longer than it was designed to, and the cost of remembering everything eventually overwhelms the cost of doing useful work. It is worth returning to the assumption we started with. A database cell looked like it held a single value, gold, with its earlier lives as iron, titanium, silver, and californium gone for good. The truth is that those earlier values were never truly discarded, while any transaction might still need them. They lingered as a chain of reversible instructions, ready to rebuild the past on request. What looks like a single value is really the visible tip of a much longer history. Multi-version concurrency control is the reason a database can let many people read and write the same data at once without ever showing anyone a half-finished, inconsistent picture. Every reader gets a stable snapshot, and the engine quietly reconstructs whatever version each one is entitled to see. The price of that guarantee is memory and the steady work of purge, and that price stays small only as long as transactions are kept short and snapshots are released promptly. The mechanism is specific to InnoDB and shifts in character with the isolation level in force, but the core idea reaches well beyond MySQL. A system that remembers its history can offer every observer a consistent view of the world. It only has to be careful about how much of that history it is asked to hold at once.